As the heading of this video states, we're going to be rationalizing the numerator. This is a process of removing the radical from the numerator. The definition is very much the same as rationalizing the denominator. There's not going to be a lot of new stuff that you're going to learn except just to see how it works. But overall, it's the same feel as rationalizing the denominator. Let's take a look at our first example. We have the square root of 11n all over 6 in our fraction. Again, realize that we're rationalizing our numerator. Please read the directions carefully, because sometimes if you don't read the directions, you're not really sure what you need to do, especially in this section. A few things that we need to understand in this problem is the fact that the index is 2. I have 111 and 1n. Again, if there are no powers, the powers are 1. In order to rationalize my numerator, the index is 2. The only way to rationalize is to match the same index. So I need to multiply top and bottom by the same thing. In this case, I have to multiply by the square root of 2 over the square root of 2. The indices must be the same in order to multiply radicals together and to smush them underneath one radical. Again, my index is 2, so I need 2 of a kind in order to get stuff out from under the radical. I have 111, I need 1 more 11. I have 1n, I need 1 more n so that everything pops out from under the radical. What I need is going to go into the radical I'm going to multiply top and bottom by. Let me show you. Again, I multiplied by another square root because this is a square root. Okay, whether the 2 is there or not, that means the same thing. I have 111, 1n, I need 1 more 11 and 1 more n. I'm going to multiply the same thing, top and bottom, the square root of 11n over the square root of 11n. Since I have 2 fractions, I'm going to turn them into 1 fraction by simply smushing the 2 fractions together. There you go. Since this index is 2 and this index is 2, whether the index there or not, I am going to smush these 2 to make one giant square root radical. Down below, the 6 is not under the radical, so the denominator is going to remain the same. I put the 11n's together. As in this case, though, what I did is I put the 11's first and then I put the n's last. I wrote it this way to show you that I have 2 11's and 2 n's. You could have written as an optional step or a different step, 11n times 11n. It is your choice as to what you want to do for that numerator. Since I have 2 11's, that comes out as an 11. Since I have 2 n's, and I need 2 of a kind again, remember that, then the n's pop out. Or again, I have 2 11n's. I have an 11n when I pop that out. The denominator remains the same. At this point, you want to determine if you can reduce the outside numbers. Again, outside numbers are numbers, or in this case, variables that are not under a radical. Those are the only type that you can really reduce. I can't reduce anything underneath a radical like this is with an 11 and an n that are outside a radical or not under a radical. Since the 6 and the 11n cannot be reduced, this is going to be your final answer. As you noticed, the radical is now in the denominator, but the whole process to get rid of the radical in my numerator. What we can do with square roots, we can do with cube roots. I have the cube root of 18t over 6. Let's see what's going on here. 18 is a big number and can be broken down. I'm looking to see what I have here. I don't want to multiply by another 18t and another 18t. I'm going to break 18 down into smaller pieces to figure out how many of these other little pieces I need. 18 is 9 times 2, or you can do 3 times 6. Either way, I broke down the 18 in terms of prime numbers. As you can see, I'm going to need different amounts of 3s, 2s, and t's. As we notice, the index is 3, meaning I need 3 of a kind. I need 3 of everything in order for it to come out from under the radical. What will happen is I will have 3 3s, 3 2s, and 3 t's under the radical. And that's what I'm trying to make, 3 of a kind, 3 of each of these numbers. So I'm going to multiply by the same index, the cube root, top and bottom. I needed 1 more 3, 2 more 2's, and 2 more t's. Again, what I did at the top, I did to the bottom. These are 2 fractions. I'm now going to make one giant fraction. I am now going to smush the cube root and this cube root together. Again, when I multiply, I only need the index to be the same, the 3, the cube root. These are going to become one giant cube root in my numerator. In my denominator, I've only got 1 3, 2 2's, and 2 t's. So I'm going to multiply all these together. This is 3 times 4, or 6 times 2, however you wish to see it. As you can see up on top, I put all my 3's together, all my 2's together, and all my t's. The stuff in pencil is the original problem. The stuff in red is what I made up above, previous couple steps, what I needed in order to get 3 2's and 3 t's and 3 3's. I circled all my grouping of 3's. Notice that I have nothing left that wasn't circled in my numerator. If you do it right, everything should be circled in terms of groups of 3's. If that's the case, your radical will go away in your next step. Also remember, if it's multiplying inside the radical, the 3's, the 2's, and the t's, then they will be multiplying once you pull them out. As you notice, I pulled out the 3, the 2, and the t just to show my groupings right here. I did not multiply them together, but you can. If you want to write this as 6t over 6 times the cube root of 12t squared, you can. And instead of writing 3 times 2 is 6 and cross out with that 6, you can cross out the 6's this way. It's what you see. You don't have to do it my way. Again, I showed you how you could do it if that's the way you want to do it. Another way to do it is to put the 1's there. This is optional. A lot of students do not go this route. This is an optional step. Most students either do this one or this one right here. I'm going to end up with 1t over 1 times the cube root of 12t squared, or you can just see it as t over the cube root of t squared. The 1's are optional. This is what the book will show. I cannot reduce this t with this t squared. This is an outside number or variable. This is under the radical, inside. Outsides do not reduce insides, or vice versa. This is our final answer to this problem. All right, on this one, what happens when you have the whole entire fraction under one giant radical? Well, according to the quotient rule of radicals, you can split this into 2 parts. When you have one giant radical with a fraction underneath, you're going to split it into 2 radicals, keeping the index the same for both of them. The square root of 3d over the square root of 5t. At this point, it's really good to remember what your directions are. This is what? This is rationalizing your numerator. Please understand that. Read the directions again, because right now I could not tell, am I rationalizing the numerator or rationalizing the denominator, just by looking at this and no directions. Once I split it into 2 radicals, remember to rationalize your numerator. I have 1 3 and 1 d. I need 1 more 3 and 1 more d to complete 2 3's and 2 d's underneath a square root sign. Again, if I'm using square roots, I'm going to be multiplying by the square root of what I need. 1 more 3 and 1 more d. I'm going to do that top and bottom. There you go. You can see what I did and how I just explained it. From 2 fractions, I'm going to write it as 1 fraction. And now what I'm going to do is I'm going to smush my numerators together. This is a square root, this is a square root, because these indices are the same. They're going to go underneath one radical. This index is 2, this index is 2. These are also going to go under the same radical, square root. And I'm just going to put these two together into the denominator. I have 3d times 3d, or again, you can put the numbers first and the letters together. Totally up to you. Again, 5t times 3d, or you can write it as the numbers first, the variables last. This is a legitimate move. This is just a commutative property. My next step is going to be to simplify. And what I mean is we're going to be simplifying the radicals. I have the index is 2. I have 2 3d's, or I have 2 3's, and I have a set of 2d's. So when I simplify, my idea, because I'm rationalizing my numerator, is to make the radical go away. So simplifying the numerator, I'm going to get 3d. Again, I have 2 3's and 2 d's, because my index says I need 2 of a kind. That's one set of 3's and one set of d's. In my denominator, I'd only have one of everything, so I'm going to multiply 5 times 3. And then the order of the t and the d will not matter when I write it. In this case, I wrote it as 15 td. You can also write it as 15 dt. This will remain in the denominator, and under the radical, there's nothing I can do with this. Do not reduce. These are outside, these are inside. Final answer. New example. We got a radical over a radical with a number on the outside, the number 7. We want to rationalize our numerator. A couple ways to go about this. If you see 14, you can do that. So you can multiply by, I need one more 14, and I need one more t. Or you can split up the 14 in terms of 2 times 7 times t. Totally up to you. As you can see, I split up the 14t in terms of 2 times 7 times t. I have 1 2, I needed one more. I have 1 7, I needed one more 7. I have 1 t, I need one more t. Again, you could have just wrote 14t for both this radical and this radical instead of splitting it apart. Again, what I need, I have to multiply top and bottom, and it has to match the index of the given radical. From here, I'm going to take these two radicals and make them into one giant radical. Notice I said that I made them into one giant radical and not into one giant fraction. You can skip that whole idea of one fraction and just simply smush them all together. So I have 2 times 7 times t times 2 times 7 times t. So you are allowed to skip steps. I skipped a step in here from 2 fractions to 1 fractions to then smushing it. I went from 2 fractions to smushing it. I have 2 2's, 2 7's, and 2 t's. And on the inside, I smooshed everything as well in their denominator, in their radical. All right, what's next? Here I put the 2's together, then the 7's together, then the t's together. On the denominator side, I put the 2's together, then the 7's, then the variables. It turns out I have 2 2's here, and up above I have 2 2's there as well. You want to reduce as much as possible, numerator and the denominator. In this case, this is unusual, but still nonetheless, you still have to reduce all radicals. So I'm going to simplify. I'm going to take this 2, take it out, one set of 2's, one set of 7's, and one set of t's. Radical will go away because everything's been circled, nothing left. Radical, again, goes away. In the denominator, I only have a set of 2's that's going to pop out. The 7, the m, and the t I did not circle. They will remain under the radical. Since the 7 is multiplying against this radical, this, when I take it out, will be 2 times 7. I took out the 2, the 7, and the t. Radical goes away. Again, I circled everything. Nothing left. I took out one set of 2's. There it is. The 7, the m, the t remain under the radical. From here, I can actually reduce my outside numbers. The 2's cancel out and the 7's cancel out as well. Again, outside numbers can only reduce with outside numbers. Same thing with variables. With this t, there's no other t in the denominator, so this t remains in my numerator. Let's see the final answer. The t remains in the numerator. The square root of 7mt stays in my denominator. Again, we rationalized our numerator. The radical went away. We just end up with a radical in our denominator. That's fine.